Alright, so for this problem, which is located on page 87, section 4.2, and the problem is labeled as problem 3 on practice 4B, okay, which is about calorimetry. We try to solve this problem. Let's see what it says. It says, what is the final temperature when 0.032 kilogram of a milk? That means we have the mass of a milk, mm, this small m means milk, which is equals to 0.032 kilograms. At 11 degrees Celsius, that means the initial temperature of the milk is given, which is 11 degrees Celsius, is added to a 0.16 kilogram of coffee. So we have another mass of the coffee, which is equals to 0.16 kilogram. At 91 degrees Celsius, we have the initial temperature of the coffee, which is 91 degrees Celsius. So we are asked to find the final temperature. That is because of thermal equilibrium, because at thermal equilibrium, both objects will come to the final temperature. So their final temperatures, the final temperature of the coffee is actually equals to the final temperature of the milk, and we label it totally as just T, because they will have the same final temperature. They become equal at that specific state, at thermal equilibrium. Okay, so you want to find T. Assume the specific heat capacities of the two liquids are the same. That means Cc, the specific heat capacity of the coffee, is equal to the specific heat capacity of the milk, which we just label it as just C. Okay, they're equal, or are the same as water. And of course, disregard any energy transfer to the liquid's surroundings. That means there is no leftover energy. So how can we solve this problem? Well, we write the principle of heat exchange, which says that the Q, the heat gained, is equal to the Q lost. Notice the negative sign, which indicates lost or looseness of heat. Now, there's important information that you have to know or indicate. So which one is the gainer, which object is the gainer, and which object is the loser? Well, we see that the milk has a lower initial temperature, while the coffee has a higher initial temperature. And we know that heat flows from higher region to a colder region. That means the coffee will lose heat while the milk gains the heat. Okay? Remember that. So basically, since T initial of the coffee is higher than the T initial of the milk, then that means the coffee loses heat. The milk gains heat. Okay? Remember that. Okay. So Q gain is then the Q of the milk. And the lost or the loser is Q of the coffee. Now we know the specific heat capacity equation, which is, just to recall, Q is equals to mc delta T. This equation calculates for us how much heat is needed to raise the temperature of an object which is about 1 kilogram by 1 degree Celsius. Okay, we can find the mass, we can find a new specific heat capacity for an unknown object, and so forth. Okay. So, Qm, if we open this equation, we get mass of the milk, C, it's just C. The change in temperature of the milk is equals to negative mass of the coffee, C. The change in temperature of the coffee. Now, notice that C and C cancels out. So we get mass of the milk, the change in temperature of the milk, is equals to negative the mass of the coffee, the change in temperature of the coffee. Okay. We substitute the masses and we solve or make a ratio. Okay. Before opening the changes in temperatures, we eliminate the masses. Okay, so the mass of the milk is nothing but 0.032 kilograms multiplied by the change in temperature of the milk is equals to negative the mass of the coffee, which is 0.16 kilograms multiplied by the change in temperature of the coffee. Now, I highly recommend to divide the bigger coefficient by the smaller coefficient. Since 0.16 is bigger than 0.032, we divide both sides by 0.032. So divide both sides by 0.032 kilograms. To make the calculations simpler and easier, 0.032. Okay, so this part just vanishes here. And this part reduces to just 5. Okay, if you divide 0.16 by 0.032, kilograms and kilograms cancels out. 0.16 divided by 0.032, we get 5. So we have the change in temperature of the milk is equals to negative 5 times of the change in temperature of the coffee. Okay. So we have this equation. Now if we open the change in temperature of the milk is nothing but the final temperature, which we label it just T due to thermal equilibrium, minus the initial temperature of the milk, equals to negative 5 times. I highly recommend opening a parenthesis because you have a negative 5 coefficient that we have to distribute later. So the change in temperature of the coffee, T minus T initial of the coffee. Now, we know that T minus T initial of the milk is just 11 equals to negative 5 multiplied by T minus T initial of the coffee is 91. So for the left hand side we can write T minus 11 is equals to negative 5T positive negative 5 times negative 91, we get 455. Okay, notice that we put this negative 5T over here and negative 11 to sum it over here. Okay, so we get 6T. Put this here, we get 6T. 5T plus 5T plus 1T, we get 6T is equals to 455 plus 11, which we get 6T is equals to 466. Okay, so divide both sides by 6 we get that finally the final temperature of both objects, so 6 and 6 cancels out, 466 or 466 divided by 6, we get about something like this. Well, approximately 77.66 degrees Celsius. So that's the final temperature of both of these objects. And that's it for this problem. Thanks for watching.